So now we're going to conclude in this section our discussion of carbohydrates. We have drawn the structures of carbohydrates as either linear or Haworth projections. The Haworth projections imply the cyclic monosaccharide is planar, but that can't be because all the atoms in the pyranose ring are sp3 hybridized. So what you're seeing here are the two conformations that the pyranose ring can assume, either the chair or the boat. The atoms that are bonded to those carbons or in the ring are sp3 hybridized. They can either be in an equatorial position, which is coplanar with the ring, or an axial position, which is parallel to the axis. Generally, if we have bulky constituent groups attached to the ring, those are in equatorial positions rather than the axial position. The chair tends to be slightly more stable than the boat. We're looking at beta glucose in the B part of this figure, and it's the B conformation of that. Beta glucose is the only aldohexose that can adopt a conformation with all of its bulky groups in equatorial positions. And this is the most common form of glucose in nature. I'm showing this to you just to remind you that these molecules, even though we're drawing them with Haworth projections or Haworth projections, are not planar but do have this configuration. I do not want you to draw them for me this way. So there are a number of derivatives of monosaccharides, and we're going to take a look at these each individually, but just to list them off. To begin with, sugar alcohols are formed by meld reductions of the carbonyl groups in sugars. Deoxysugars, constituents of DNA, have one or more hydroxyl groups that are replaced with a hydrogen atom. Sugar esters, we're going to look at ATP, for example. These are phosphate esters of glucose and fructose. Aminosugars are going to contain an amino group in place of a hydroxyl group. We'll look at D-glucosamine, which is an amino group at C2. We can have acetals, ketols, and glycosides, and these are the basis for oligo and polysaccharides. We'll look at the condensation reaction that forms the glycosidic bond. Also not listed here, well actually no, I did add it, sorry, are the sugar acids, which involves the oxidation of an aldose to a carboxylic acid sugar. Now we need to define what a reducing sugar is, and thus a non-reducing sugars. Reducing sugars are going to have a free anomeric carbon that can be oxidized by oxidizing agents, and some are listed here: peroxide, ferrocyanide, some metals, copper ion, silver ion. These redox reactions convert the sugar to a sugar acid. Glucose is a reducing sugar, so these reactions are the basis for the diagnostic test for blood sugar. Sucrose is a non-reducing sugar, and we'll look at those features momentarily. So here we're looking at the oxidation of that aldehyde head group in the first structure at the top. We're oxidizing C1, and from that we get a carboxylic acid in that, replacing that aldehyde head group, and this is D-gluconic acid. If we oxidize C6 at this position, we get a carboxyl group on the 6th carbon, and this is glucuronic acid. You're not responsible for the names of these acids, but you do need to know what comes from the oxidation of these groups. We could also oxidize both C1 and C6 to get glucaric acid. So remember, oxidation is going to be the gain of carbon to oxygen bonds and the loss of hydrogen. Sugar alcohols, sorry, I'm so tongue-tied again, or alditols. These are sweet tasting and actually are used in sweeteners for gum. D-xylitol, I'm sure you've heard of. Glucatol is, common name is sorbitol, and here we have D-mannitol. This too involves the reduction of those carbonyl groups of aldoses and ketoses. Deoxysugars. Again, these are monosaccharides that have a hydrogen in place of one of their hydroxyl groups. Probably the most familiar to you is 2-deoxy-alpha-D-ribose. So remember, ribose is one of our pentose sugars, and rather than a hydroxyl group at C2, we have a hydrogen. So that's where that 2-deoxy comes in. A couple other examples here. I'm not going to go through those, but again, we've got hydrogens replacing hydroxyl groups. These might also be found in glycoproteins and polysaccharides. Sugar esters. So these are phosphate esters of glucose, fructose, and other monosaccharides that are metabolic intermediates. So we're going to see these in some of our pathways, and actually coming up after your second exam, we'll start discussion of glycolysis, in which we'll see glucose 1-phosphate and alpha-D fructose 1,6-bisphosphate. So these are very important in metabolic pathways. And you'll see that we have these phosphate groups that have been substituted here. So remember, this is an ester. Amino sugars. So we have an amino group that is replacing either a hydroxyl group or a hydrogen. Actually, these are hydroxyl groups. Beta-D-glucosamine, you're probably very familiar with. In the U.S., it's one of the most common non-vitamin, non-mineral dietary supplements that are used by adults. It's marketed to support the structure and function of joints or osteoarthritis. It may help prevent the cartilage degeneration. Some people swear up by it, some others don't get any benefit, but it's one of the most abundant monosaccharide derivatives. This, remember, galactose or galactosamine is a C4 epimer of glucose. Glucosamine is also a precursor to the synthesis of glycosylated proteins and lipids, and we'll see that. It's part of the structure of chitin, which we'll look at. That chitin is part of the exoskeleton of crustaceans and other arthropods. So we mentioned disaccharides earlier. In the first video, we're going to take a closer look at those. But just to refresh your memory, they are the simplest of the oligosaccharides. We've got 2 monosaccharides that are linked by glycosidic bonds. Again, reminder that we call those individual saccharide units residues. And each of these, except for sucrose, is going to possess a free unsubstituted anomeric carbon, making it a reducing sugar. Sucrose is not a reducing sugar because it does not have that free anomeric carbon. So I mentioned to you the 3 most common disaccharides in the first video: lactose, maltose, sucrose. There are 2 more here cellobiose and isomaltose. You are not responsible for structures for the last two of these, but you are responsible for the structures of the three most common disaccharides. The only one of these that is not a reducing sugar is sucrose again. Here's that anomeric carbon, and it is not free. So it doesn't have that hydroxyl group attached to it like these structures do. Lactose occurs naturally only in milk. Its concentration ranges between 0 and 7%, and it is composed of a residue of beta-D-galactose and D-glucose. And when we look at this notation, the galactose B beta 1,4 glucose. So the linkage is between carbon 1 on galactose and carbon 4 on glucose. Lactose can't be directly absorbed in the bloodstream, so that means we need an enzyme to break it down, break that glycosidic bond to free those monosaccharides up, and that enzyme is lactase. Lactose intolerance results from the lack of this enzyme. Maltose, our second disaccharide here, is composed of two glucose units. Again, not again, this is an alpha 1,4 linkage. And so compare the way the beta linkage is represented to the way the alpha linkage is represented. So remember that hydroxyl group in the beta position is up, so we have this angled bond here with that O, and in the alpha position, that hydroxyl group is down. The enzyme maltase is responsible for cleaving that glycosidic bond. Sucrose is composed of a residue of glucose and fructose, and this is, again, this linkage is through carbon 1 on glucose, and this is a beta 2 fructose. Sucrase is the enzyme responsible for hydrolyzing the glycosidic bond here, and then I'll just mention what cellobiose is a result of. This is a glucose, or actually two glucoses, but the difference between maltose and cellobiose is that linkage here is beta 1,4. So this is comes from the hydrolysis of cellulose. So starches are basically polysaccharides used to store monosaccharide units. There are two forms, amylose and amylopectin. Another word for this is a glycan. Most starch in nature is 10 to 30% amylose and 70 to 90% amylopectin. There are branches in amylopectin, about every 12 to 30 residues, and this is important because we'll be comparing that to another polysaccharide that has branching, and that is glycogen. Amylose has alpha 1,4 links and one reducing end. There is no branching. The branches in amylopectin are alpha 1,6, and we'll take a look at that structure. So again, these polysaccharides in the form of starch have several uses, energy storage. They could be structural components or even protective molecules. So again, amylose and amylopectin are energy storage molecules in plants, and here are their structures. Amylose, again, it looks linear here. It's actually, we'll see another representation of the structure that shows it's actually rather helical in formation. And here is amylopectin with a branch coming off of it. So this is the one 6 linkage. And again, those branches occur every 12 to 30 residues. Now, when it comes to saccharide storage in animals, the molecule is called glycogen. Glycogen consists of about 10% of the liver mass and 1 to 2% of muscle mass. So this is really just a short, it's energy storage, but it can be consumed relatively quickly. So if we have excess intake of carbohydrates, we're going to further store that as fat. So again, glycogen is stored for energy, only its energy supply is relatively small. The only difference between glycogen and amylopectin is the frequency of the branching. The branches are the same, alpha-1, 6, but these branches are every 8 to 12 residues. You don't need to worry about this. I should have actually probably deleted that. So the composition of structural polysaccharides is similar to storage polysaccharides, but small structural differences can greatly influence the properties. Starch and glycogen linkages consist primarily of alpha-1, 4 linkages or alpha-1, 6 for those branch points. But cellulose, which is structural, contains beta-1, 4 linkages, and that's important. So cellulose is a structural polysaccharide. It's the most abundant polymer in nature, found in the cell walls of nearly all plants. Wood and bark of trees are insoluble because of those highly organized structures formed by cellulose and lignin. Cotton is almost pure cellulose, and we have derivatives of these polymers or cotton acetates of cellulose, which is used in clothing. So this is a comparison of the structural differences between amylose and cellulose. So this is the structure that shows that this structure is really not linear as it looks when we viewed it previously. So it forms this kind of helical. So this will come up in here. Cellulose is linear. So this is helical, this is linear. Cellulase is the enzyme required to hydrolyze the beta-1, 4 linkage, and we don't produce that enzyme. So we cannot digest cellulose, though. So animals that can digest cellulose have bacteria that secrete this enzyme in the first large compartment in the stomach. Those would be the ruminant animals, cows, so forth. We kind of usually refer to that as chewing their cud. So that's what is happening there. This is just a comparison of the structures of cellulose, chitin, and mannan. Chitin, remember I said, is in the exoskeletons of crustaceans, and it contains glucosamine, or it has that derivative attached to the chain of saccharide units. Finally, drug research. So there are a variety of diseases that have been treated with sugar-based therapies. You may recognize some of these names, maybe not all. Vancomycin or vancomycin is an antibiotic. It's usually used as a last resort, but this is a glycopeptide, so it has a saccharide unit in it, and this inhibits the peptidoglycan in the bacterial cell wall. Eli Lilly has produced that. Thought there was one other you might recognize. Cerezyme, maybe you've heard of, degrades glycolipids, so this can compensate for enzyme deficiencies that cause Gaucher's disease. But at any rate, this is just to give you an idea of what type of products that have been made from basically sugar, proteins that contain sugar of some sort. Okay, so now we're going to move on to lipids.